Science.
This is episode 4 of Physics Astronomy Guys. I'm Alan.
And I'm Ian. This is a show about science.
To start off today's episode, we're going to answer the question from last episode. And that was, why is it that stars appear to twinkle much more on the horizon than they do at the zenith? So the answer is, anytime light passes through any sort of medium, be it the atmosphere or water, or anything like that, it gets obstructed a little bit. There's dust in the atmosphere that causes it, also just light bending as it passes through the medium. And when it gets obstructed, the brightness dims and then gets brighter. So that's why it appears to twinkle. Now, on the horizon, you're looking through about 37 miles of thick atmosphere. It's about where the atmosphere starts to become much thinner, is about 37 miles tangentially. But if you look straight up at the zenith, you're only looking through about 5 miles of actual thick atmosphere if you're on sea level. And that's because even though the atmosphere is technically defined to go up to 100 kilometers or 62 miles, really most of the atmosphere is about 5 miles. So there's far more atmosphere to obstruct the light and cause it to appear to twinkle on the horizon than at the zenith.
Yep. Thank you all who answered that in the comments in our last episode, which, sorry, got split into 2 parts. It was a little too big for YouTube with just one movie. And the first person who answered that name will be right here. Thank you. And we will now move on to our current events for the day.
Okay, so do you want to do the first one, or should I take it?
Okay, the Discovery is going to be launched on February 24th. And so, watch it, I guess, on NASA. It's going to be cool. There's only 2 more after that, unfortunately, I think. And so, now our next current event.
So there was an object called NEOWISE, which I believe stands for Near Earth Object Wide Field Infrared Survey Explorer. And basically what it was doing is it was scanning the sky for asteroids and comets. And recently it completed its entire scan, and the results were it found 33,000 more asteroids in the main asteroid belt. It found a total of 134 near-Earth objects, or NEOs, and it found 20 new comets. So a lot of material, a lot of data gathered by that instrument.
Yep. And so now we'll move on to our topic of the day, which is...
So oftentimes in science fiction movies, you will see entire planets blow up. So we're going to discuss the actual physics of that actually happening. So in order to blow up an entire planet, the main force holding it together when you have something as large as a planet is the gravitational binding energy, or the energy holding it together, of that planet. You also have van der Waals forces and you have chemical bonding, but for a planet it's mainly the gravitational binding energy. So in order to blow up the entire planet, you would have to overcome that gravitational binding energy. And the gravitational binding energy is found by taking 3/5 of the gravitational constant multiplied by the mass of the body squared, and then dividing that number by the radius of the body. So for something like the Earth, the gravitational constant is about 6.67 times 10 to the negative 11, and then the mass of the Earth is about 5.98 times 10 to the 24th. So you square that, you get like 3.56, something like that, times 10 to the 49th. Then multiply that by 6.67 times 10 to the negative 11. That gets you about 2.1 times 10 to the 39, something like that. And divide by the radius of the Earth, which is 6.378 times 10 to the 6th, right, meters?
Mm-hmm.
So you come up with a total number, and then you have to multiply that by 3/5. So you come up with a total number of about 2.5 times 10 to the 32nd, I believe. So you have 2.5 times 10 to the 32nd joules holding all of Earth together. So in order to blow up the Earth, you need at least that much energy, even disregarding chemical bonding, to blow up the Earth. Now, oftentimes people will ask about nuclear power to do so, but really the typical nuclear bomb doesn't have nearly enough energy to do it. It would actually need about 10 trillion nuclear bombs to blow up the Earth. So, of course, we don't have nearly enough to do so.
So now if people say that could blow up the Earth or completely disintegrate it 100 times over, then you can tell them to watch this video and we'll explain why that is wrong.
The reference there is we once had a social studies teacher that said that.
Yes, he thought that all the nuclear bombs could completely disintegrate the Earth 100 times over.
Of course, the physics for that doesn't work.
No. And so we will move on to the second part of the viewer choice question, which is the Gemini missions. And so with the Gemini missions, we will start off with Gemini 1, which was unmanned, and it was just the first test flight of the Gemini project.
So it lasted a total of 3 days and 23 hours, and it's really just the first test flight. The mission date was from April 8th through April 12th, 1964.
And then that brings us to Gemini 2, which was also an unmanned Gemini mission. And that mission was a suborbital flight that they just wanted to test the heat shield on the capsule on top.
So its duration was only 18 minutes and 16 seconds, just because, of course, they weren't flying it. They were testing the heat shield, so you just need the atmosphere exit and reentry. And that was on January 19th, 1965.
And here we will show a picture of the Gemini 2 capsule that is on display at the Air Force Space and Missile Museum.